Hi everyone. This video is going to cover the final exam review that you can find on YouTube. As you found the link. Below in the description you can find a copy of the questions, a copy of the answers, and you can also find the times listed out, and at least on a computer you can click on those times and then it'll take you directly to that problem. I do want to remind you, and at the same time answer question 1, it said, should the practice midterm be reviewed for the final? The answer is yes. The final is cumulative, so make sure you're reviewing the practice midterm video as well. Hopefully we've made these into a playlist and you're looking, you can just click on it. It should actually be on your screen right now. So that's basically that. The other thing I want to remind you is you do get a cheat sheet for the final exam. I strongly recommend you take advantage of that cheat sheet, and as we go through this exam I may give you some tips and tricks of things to put on your cheat sheet, but I'm probably a bad person to ask about that. But anyway, if something occurs to me, I will mention it as we go through. Alright, so let's start with the first actual problem. So the first problem is a review problem, kind of more from the first half of the semester, but it says what kind of property is density? And it has intratensive and monotensive. These are just made up words. So the choices are intensive or extensive. And intensive means a property that's independent of the amount. Extensive means a property that's dependent on the amount, and I have this all written out on the answer key. I'm not going to write it again here. So an intensive property is independent of the amount. Let's think about density. Density, whether you have a cup full of water, a bathtub full of water, or a lake full of water, the density of water is approximately 1 gram per milliliter in all cases. So density is an intensive property. Boiling point would be another intensive property. For example, the water boils at 100 degrees, whether it's in a lake or a bathtub or a cup. Extensive property depends on the amount. And in this case, mass and volume are the two most common examples. The mass of water in a cup and the mass of water in a lake are very different. Same with the volume. So those are extensive properties because they depend on the amount. Number 3 says, how many of the following are at least slightly soluble in hexane, C6H6? And what we need to remember to figure this out is like dissolves like. And what this means is polar and ionic solutes dissolve in polar solvents. A common polar solvent is water. Hexane, which only contains carbon and hydrogen, is non-polar. So it will dissolve things that are like it, remember like dissolves like, which are also non-polar. So let's look at sodium carbonate. Sodium carbonate is ionic. It's going to dissolve in things like water. It is not going to dissolve in hexane. Iodine is non-polar. So since it's non-polar, it will dissolve in non-polar hexane. NaOH, it's again ionic, contains a metal and a polyatomic ion, just like sodium carbonate. So it is not going to dissolve in a non-polar solvent. It would dissolve in a polar solvent like water. Number 4 says, according to the solubility guidelines, which of the following is soluble in water? So we need to remember our solubility rules. Solubility rules generally apply to anions, although the 1A metals and ammonia are covered, which are always soluble. But they generally apply to anions, the negative ions. So hydroxides. Hydroxides are generally insoluble. Magnesium hydroxide is no exception. Carbonates. Carbonates are generally insoluble, and magnesium carbonate is not an exception. Chlorides are generally soluble, and magnesium is no exception. The exceptions there are silver, mercury, and lead, not magnesium. So this one is soluble. I would strongly recommend that you use your cheat sheet to write the solubility rules. You can get those from your textbook, or if you don't have a textbook, simply Google solubility rules for ionic compounds, and you can copy and paste them into your cheat sheet. Question number 5 says, when magnesium sulfate is dissolved in water, what is present in solution? Well, if you take magnesium sulfate, solid, and you dissolve it in water, you get magnesium ion, which is Mg2+, which is aqueous, and sulfate is a polyatomic ion, which is SO4 which is aqueous. So you have magnesium, a 2A metal, so has a +2 charge, and sulfate, SO4 It would not be a bad idea to put on your cheat sheet the polyatomic ions. To answer this question, the answer is choice letter A. Question 6 asks, how many moles of magnesium are in a 315 gram sample? Well, we want to convert from grams to moles, so we need to use the molar mass. So we take 315 grams of magnesium times, from the periodic table, we can find that 24.31 grams of magnesium is equal to 1 mole of magnesium. When you do that math, you find that there are 13.0 moles of magnesium in this 315 gram sample. Question 7 says, how much magnesium chloride in grams is needed to make 75 milliliters of a 0.810 molar solution? So in order to convert from milliliters to moles, we have to first convert to liters. So we want to take liters of this solution, MgCl2, and convert that to moles of MgCl2, and then finally to grams of MgCl2. So this is divided by 1,000, 0.0750 liters of solution. So we start with our 0.0750 liters of MgCl2 times, well, we know the molarity of this solution, that we know that in every 1 liter there's 0.810 moles. We want liters to cancel out, so we put 1 liter of MgCl2 on the bottom, and on top we can put the 0.810 moles of MgCl2 times, we now want to convert it to grams, so we add up magnesium and 2 chlorides, molar mass, and we find that 1 mole of MgCl2, which we want to cancel out, so we put it on the bottom, is equal to 95.21 grams of MgCl2. When you do all that math, multiply by the top, divide by the bottom, repeat until you're done, you get 5.78 grams of MgCl2 being required to make this solution, and that is choice letter A. Question 8 says, what type of reaction is the following reaction? Well, we have MgCl2 plus NaOH yields MgOH2 and NaCl. So magnesium goes with hydroxide to form magnesium hydroxide, and sodium goes with chloride to form sodium chloride. This is a double replacement reaction. Magnesium replaces sodium, and sodium replaces magnesium, or chloride replaces hydroxide. However you want to think about it, both things are replaced, so this is called a double replacement reaction. Number 9 says, in a blank reaction, 2 or more elements or compounds form one product. So this is A plus B yields AB. This is called a combination reaction. So we have 2 things forming one thing, so 2 or more. You could have A plus B plus C yields ABC, or A plus B yields A plus B. In either case, it's a combination reaction. We combine multiple things to form one thing. We call that a combination. Number 10 says, if a compound has an empirical formula MgCl2 and contains 4.1 grams of magnesium, how many grams of chlorine does it contain? Well, if the empirical formula is MgCl2, we know there's 1 magnesium for every 2 chlorines. But that's 1 mole of magnesium for every 2 moles of chlorine, not grams. So we need to convert from grams of magnesium to moles of magnesium. Then we can figure out how many moles of chlorine we're going to have. It's twice as many as the moles of magnesium. And then we can convert it back to grams of chlorine. So we have to do a lot of steps in order to figure this out. So starting with 4.1 grams of magnesium times, well, 24.31 grams of magnesium is equal to 1 mole of magnesium from the periodic table, times, for every 1 mole of magnesium, because it's 1 in the empirical formula, there are 2 moles of chlorine, because it's 2 in the empirical formula. Now that we have moles of chlorine, we simply have to convert it back to grams using the molar mass. So we have 1 mole of chlorine on the bottom, 35.45 grams of chlorine on the top. Multiply by the top, divide by the bottom, repeat all the way to the end, and we get 12 grams of chlorine in this to answer this question, which is choice letter D. Question number 11 asks us, how many of the following vocabulary terms are defined correctly? So recrystallization, a separation or purification technique that uses differences in solubility of desired compound and the solubility of the impurity in a solvent or mixture of solvents at different temperatures. That is absolutely correct. In recrystallization, we dissolve the bulk mixture at high temperature. We then cool it down. The compound of interest, the product, crystallizes out, and the impurity remains dissolved in the solution. At least that's the goal. Organic compounds. Compounds containing carbon, hydrogen, and often in combination with oxygen, nitrogen, and other elements. That is true. Double displacement reactions. Two reactants form a single product. From a question above, we learned that this was called a combination reaction, not called a double displacement reaction. So this is incorrect. So the answer here is 2 of these 3 are true. So question 12 says, use the following reaction showing the synthesis of acetaminophen to answer the next 2 questions below. And I'm just going to move this up so we can see both the questions. First it says, what is the limiting reagent? And then it says, what is the theoretical yield of acetaminophen? Well, the good news is we only have to do the math once. The bad news is we kind of have to do it for both p-aminophenol and acetic anhydride. So we're given amounts of p-aminophenol and acetic anhydride, and we're asked to find out how much acetaminophen we're going to form. So essentially what we have to do is we have to find out how much acetaminophen we can form from all of our p-aminophenol, and how much we can form from all of our acetic anhydride, and however much acetaminophen we can form will give us our theoretical yield, whichever one's less, because that reagent will run out. The limiting reagent is which of these 2 gives that amount of acetaminophen. So a couple things. I'm going to call this in my stoichiometry p-amino. I'm going to call this AA, and I'm going to call this ACE, just so I don't have to write the whole word 6 times each. So that's basically that. So I'm going to start with p-aminophenol. I want to convert from grams of p-aminophenol to moles of p-aminophenol to moles of acetaminophen, I'm going to call it ACE, to grams of acetaminophen. So I want to find out how much acetaminophen I can make from all of my p-aminophenol. So starting with 5.0 grams, because it says 5 grams, of p-aminophenol times the molar mass is given, so I want to convert it to moles, so I put the molar mass on the bottom, 109.1 grams of p-aminophenol, and on top, 1 mole of p-aminophenol. Now I want to convert it to moles of acetaminophen. Note that this looks complex, but they're not shown here. I'm going to write them. These are all 1-to-1. So all we care about is the stoichiometric coefficients. We don't care about how complex these things look. So all we have to do is put for every 1 mole of the p-aminophenol, we generate 1 mole of acetaminophen times. Now when you want to convert to grams of acetaminophen, from moles of acetaminophen to grams of acetaminophen, we have to use the molar mass. So 1 mole of acetaminophen is 151.2 grams of acetaminophen. Multiply by the top, divide by the bottom, repeat to the end, and we find that we'll make 6.9 grams of acetaminophen. What this means is if we use all 5 grams of p-aminophenol, we'll make 6.9 grams of acetaminophen. But we have to repeat this whole process with acetic anhydride to figure out if we'll make more or less. Then we can figure out how much we'll actually make. So in this case, I'm given milliliters. So I have to convert from milliliters of acetic anhydride to grams of acetic anhydride. It's an extra step, but fortunately, I'm given the density. The density will allow me to convert from milliliters to grams. Then it's the same thing. Once I have mole or grams of acetic anhydride, I can convert it to moles of acetic anhydride, then to moles of acetaminophen, and then finally to grams of acetaminophen. So it's one extra step at the beginning. So starting with 3.0 milliliters of acetic anhydride times, I know that there's 1.08 grams in a milliliter. So I put the 1 milliliter on the bottom. I put the 1.08 grams on the top. and now I have grams of acetic anhydride. Now it's exactly the same as the previous one. I want to convert those grams to moles. This time, of course, I use the molar mass of acetic anhydride, not the molar mass of aminophenol, p-aminophenol. So I put the 102.1 grams of acetic anhydride on the bottom, 1 mole of acetic anhydride on the top, times. I'm going from moles of one thing to moles of another. I need to use the balanced chemical equation. It's still 1 to 1. So 1 mole of acetic anhydride gives me 1 mole of acetaminophen. Then the last step is the same, because in both cases I'm going from moles of acetaminophen to grams of acetaminophen, moles of acetaminophen to grams of acetaminophen. So if it's the same conversion, I can use the same conversion factor. I put the 1 mole of acetaminophen on the bottom and the 151.2 grams of acetaminophen on the top. Multiply by the top, divide by the bottom, repeat to the end, and you get 4.8 grams of acetaminophen. So how much are we going to make? Are we going to make 6.9 grams with all of our p-aminophenol, or are we going to make 4.8 grams with all of our acetic anhydride? The answer is 4.8 grams because it's less. This is the most acetaminophen I can make with all of my acetic anhydride. Said another way, when I make this much acetaminophen, I have no acetic anhydride left. If I have no acetic anhydride, I can no longer complete this reaction. So this is the theoretical yield, which answers question number 13, which is 4.8 grams. This acetic anhydride, the thing that leads to the theoretical yield, the one that runs out first, is the limiting reagent, and this answers question number 12. So we were able to answer both questions by doing this twice. So this is a limiting reagent and theoretical yield question, actually 2 questions applied to an organic reaction. Remember that in the lab, you did this for aspirin. Question 14 asks, why is it important that the impurities in a sample be soluble in cold solvent when performing a recrystallization? So in a recrystallization, we take the bulk product, and you did it with aspirin, and you had some impurities, such as, in this case, you used salicylic acid, and you had some impurities in there, and you heated it all up, and you dissolved all the aspirin and all the impurities. You then cooled the solution down. When you cooled the solution down, you recrystallized the aspirin, but the impurities, which there was much less of, remained soluble in the organic solvent. You used ethanol and water. So that's basically that. So basically what this says is, why is it important that the impurities in a sample be soluble in cold solvent when performing a recrystallization? So that the solvent does not need to be heated. No, it needs to be heated to dissolve the bulk solid. So that the impurities remain dissolved in solution when the solution is cooled. That's what's important. The impurities need to remain dissolved. So that way, what crystallizes, in your case, was pure aspirin, and the salicylic acid remained in the solvent. So the impurities will no longer be soluble in hot solvent. That doesn't make any sense, and it is not important. We found why it's important, so the answer here is choice letter B. Number 15 says, while determining the melting point of an impure solid product, what is one expected deviation from the melting point of the pure sample you would likely observe? So there are 2 deviations for impure solids, as written on the answer key. One is they have broadening of the melting point range, which is choice letter A. The other one is they have a lower than expected melting point. So if a solid is impure, it will have a lower than expected melting point and a broadening of the melting point range. That is something you could write on your cheat sheet if you don't already have it in your memory. Question 16 says, which of the following indicates precise data? This means low variability. How we calculate variability or reproducibility of the data is by the RSD. So precise data has a low RSD. Accurate data, which is data that is very close to the expected value, has a low % error. So in this case, we care about RSD, and we want the RSD to be low. 1.2 parts per thousand is low. 952 out of 1,000, not so much. So precise data will have a low RSD. Note that the % error being low means that the data is accurate. And It might be a good thing, but it's not precision. So make sure that you're aware of the difference between accuracy and precision. Again, it's something you could put on your cheat sheet. Question 17 says, how much of a 6 molar HCl solution does a student need in order to make 125 milliliters of a 2 molar solution? You are probably very familiar with dilutions by this point. So your equation here is C1V1 equals C2V2. The initial concentration is 6 molar times the initial amount. That's what we don't know. So we're trying to find out the initial amount of the 6 molar. It says how much 6 molar do you need? What are you trying to make? Well, you're trying to make 2 molar. And how much? You're trying to make 125 milliliters. So 2 times 125 divided by 6, and you find that V1 equals 41.7 milliliters. So if you take 41.7 milliliters of 6 molar HCl and you dilute it to a total volume of 125 milliliters, it will now be 2 molar HCl. We've done this many times in the lab. Here it's applied to HCl, but the idea is the same. Depending on, it doesn't really matter what you're diluting. Question 18 says, what is the molarity of HCl if it takes 10.87 milliliters of 0.1 molar NaOH to titrate 5 milliliters of the HCl? So here we need a balanced chemical equation. So we have HCl aqueous plus NaOH aqueous. It's a double displacement reaction. We get water and NaCl. So what we end up with is NaCl aqueous plus H2O liquid. Now we actually want to be able to do the stoichiometry. Well, we need a plan of attack. We need to start with the liters of NaOH, because we have the volume of NaOH and the molarity, so we can find the moles of NaOH. That will help us to find the moles of HCl using the balanced chemical equation, and then we can divide by the volume in liters to find the volume, or to the molarity of the HCl. So we need to convert this to liters. 0.01087 liters, just divide by 1,000. Once we have liters of NaOH, we can convert it to moles of NaOH because we have a molarity. We can then convert it to moles of HCl because we have a balanced chemical equation. We can then take those moles of HCl and divide by liters of HCl. And moles per liter gives us the molarity of, in this case, the HCl. So let's start with 0.01087 liters of NaOH times, we want to use the molarity to convert that to moles. Well, this tells us that it's 0.1 molar. That means in every 1 liter of NaOH, there's 0.100 moles of NaOH. That's moles per liter. Times. Now we want to convert to moles of HCl. Well, we know it's 1 to 1. For every 1 mole of NaOH, it requires 1 mole of HCl. Now we need to divide by the volume in liters. To divide, we put a unitless 1 on top. We take this 5 milliliters, we divide it by 1,000, 0.0500 liters, 0.00500 liters. And when you do all that math, you find that the HCl is 0.217 molar. So that is a acid-base stoichiometry type of problem. Question number 19 says, what is the concentration of NaOH if 14.32 milliliters of NaOH is required to completely react with 0.2561 grams of potassium hydrogen phthalate, KHP? The reaction of, it should say, KHP and NaOH is 1 to 1, and the molar mass of KHP is given. So this should say that. All right, so we're given a mass of KHP, we're given a volume of NaOH, and we're asked for the concentration of NaOH. This is similar to question 18, but it's a little bit different. So if you haven't seen question 18, I would start there. So here, we're going to go from grams of KHP to moles of KHP, then to moles of NaOH. We know it's a 1-to-1 stoichiometry, so we can convert from 1 to the moles of KHP to moles of NaOH. And then finally, we're going to take those moles and we're going to divide by the liters of NaOH, and moles divided by liters gives us the molarity of the NaOH. So there's a couple things we need to do. All right, first we need to convert this to liters because we're going to use it eventually. So I'm going to divide that by 1,000, 0.01432 liters of NaOH. Now we can start with the grams we're given. So we have grams of KHP, 0.2561 grams of KHP, times, we want to convert it to moles. Well, we're given the molar mass, 204.23 grams of KHP on the bottom, and on top, 1 mole of KHP. Now we can convert it to moles of NaOH. We know it's 1 to 1. So for every 1 mole of KHP, we need to react 1 mole of NaOH. Finally, we need to divide by the volume in liters. To divide, we put a unitless 1 on the top, and then we plug in the volume in liters, 0.01432 liters. So then we'll have moles of NaOH over liters of NaOH, which gives us the molarity of NaOH. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, repeat till the end, and what you find out is it's 0.08757 molar NaOH, which in this case is choice letter D. Question 20 says, what is the experimental molar mass of a monoprotic acid HA if a solution containing 1.862 grams is titrated completely with 27.21 milliliters of 0.3369 molar NaOH? Hint, 1 mole of the acid HA reacts with 1 mole of sodium hydroxide. So we have HA aqueous plus NaOH aqueous. Na goes with A, H goes with OH to make water. We get NaA aqueous plus H2O liquid. And we want to find the molar mass. Well, normally if you want to find a molar mass, you look it up on the periodic table. But experimentally, molar mass is grams of, in this case, HA, divided by moles of, in this case, HA. Well, the grams of HA are given right in the problem. So we need a way to find moles of HA. How we're going to find moles of HA is stoichiometry. Very similar to questions 18 and 19. So if you haven't viewed those, view those first. So how do we do that? Well, we start with this in liters, which is divide by 1,000, 0.02721 liters of the NaOH. So we're going to go from liters of NaOH. We're going to use the molarity of the NaOH and the liters to find moles of NaOH. And then we can convert that to moles of HA. If we have moles of HA and we have grams of HA, we simply plug in and we find the molar mass. So starting with 0.02721 liters of NaOH times. This is 0.3369 molar, which means that for every 1 liter of this NaOH solution, there's 0.3369 moles of NaOH times, now we want to go to moles of HA. Well, for every 1 mole of HA, there's 1 mole of NaOH. So an NaOH to cancel out, so I put 1 mole of NaOH on the bottom and 1 mole of HA on the top. When you do this math, you find that this is 0.009167 moles of HA. Now I have both my values. I take the 1.862 grams of HA divided by the 0.009167 moles of HA, and I find that the molar mass of, in this case, HA is equal to 203.1 grams per mole, which is choice letter A in this case. So, a lot of work. You did this in the lab for citric acid, but it's a lot of work, but it is an experimental way to determine the molar mass. Question 21 says, how much solid sodium carbonate is needed to make 100 milliliters of a 0.04 molar sodium carbonate solution? And then it gives the molar mass of sodium carbonate. You actually did this in the lab. You made 100 milliliters of a 0.04 molar sodium carbonate solution when you were doing experiment 10. So to do this, we need to convert from liters of Na2CO3 to moles of Na2CO3, and then finally to grams of Na2CO3. Starting with the volume in liters, so 0.1000 liters. So 0.1000 liters of Na2CO3 times, for this particular solution, there's 0.04 moles in 1 liter. So we put 1 liter of Na2CO3 on the bottom and 0.0400 moles of Na2CO3 on the top. Times, now we want to convert to grams. We have the molar mass, so we put 1 mole of Na2CO3 on the bottom. And on top, the molar mass, 105.99 grams of Na2CO3. Do all the math, and you find that there are 0.424 grams of Na2CO3 required to make 100 milliliters of this particular solution. And that is choice letter B. Question 22 says, which of the following solutions would have the highest conductivity reading? The solvent of all the solutions is water. So if we have 0.1 molar Na2CO3, 1 molar Na2CO3, pure water, and they should have all the same conductivity. Well, as the amount of ionic compounds in water goes up, so too does the conductivity. So in this case, the highest concentration of sodium carbonate, an ionic compound, dissolved in water, will have the highest conductivity. Pure water should theoretically have a conductivity of 0, although very pure water is hard to come by. 0.1 molar will have something much above 0, but 1 molar is 10 times more concentrated, so it should have an even higher conductivity than the 0.1 molar. Question 23 says, what is the solid product of the following reaction? Well, sodium goes with Cl and Ca goes with CO3. Again, you should have your polyatomic ions on your cheat sheet. So we have Na plus and Cl minus, we cross them, and we get NaCl. This is going to be aqueous. We have Ca2 plus and CO3 2 minus. Calcium's in 2A, so it's 2 plus. Carbonate is a polyatomic ion, you should know. Don't forget, 1A is plus 1, 2A plus 2, 3A plus 3, 5A minus 3, 6A minus 2, and 7A minus 1. So this is the common charge on the ions based on the periodic table. Anyway, to finish this, we cross them, but since they're both 2, we cancel them out. So it's not Ca2CO3 2, it's simply CaCO3, which is chalk. This is the solid. Because of the solubility rules, carbonates are generally insoluble. So calcium carbonate is the solid product that is formed. If you wanted to write this out as a complete reaction, you would get CaCO3 solid plus 2NaCl aqueous. And that would be the complete reaction. So, question 24 says, how many of the following have a positive formal charge on the central atom? If you're still unsure how to do Lewis structures, please go back and watch the videos on Lewis structures that we sent out to you with experiment 11. In the interest of time, I could spend 20 minutes writing these Lewis structures out, but I do that in that other video. So here, I'm just going to directly write out the Lewis structures, and we're going to take a look. I strongly recommend you do this before I do it, and then check your answers to see if they're the same as mine. So NH4 plus is going to look like this. We have to put nitrogen in the middle because hydrogen can't be in the middle, and this is the charge. So this one has a plus charge on the central atom. Nitrate's a tough one. Nitrate actually has two negative formal charges and a positive formal charge. And I go over this exact one in that other video. So I recommend you watch that if you're not sure how to do it. The reason for this is you can't make this extra double bond and extinguish these formal charges because nitrogen can't expand its octet. So nitrogen does actually have a formal charge, a positive formal charge on the central atom. Sulfate, the best Lewis structure looks like this. I also go over sulfate on that video. So you could watch the video on Lewis structures. Again, we sent it out when you were doing experiment 11. If you want to find it in the announcements, okay? And this is the best Lewis structure of sulfate. There's no positive charge on the central atom. Finally, NFO2. NFO2 is the same as NO3, except for N is bonded to an F and two oxygens, and one of them is a double bond, and one of them is a single bond. So the single bonded oxygen has a minus formal charge, the double bonded oxygen has no formal charge, and the fluorine has no formal charge. But the nitrogen wants to have 5 electrons, it only has 1, 2, 3, 4. So it is a positive charge. So it turns out that 3 of these have a positive charge on the central atom. If you were unable to draw these 3 Lewis structures, I strongly recommend that you go back to that other video and you practice your skills. I just don't want to spend a lot of time here when I have these on the other video. This one's pretty straightforward, and this one's exactly like this one. So that is basically that. So question 25 and 26 are about the same species, SF4, same compound. So the first question, 25, asks, give the number of valence electrons. Well, sulfur has 6, and because it's in 6A, and fluorine has 7, but there are 4 of them, and it's in 7A. So 6 plus 4 times 7, again, sulfur's in 6A, so it has 6. Fluorine's in 7A, so it has 7, and there are 4 fluorines, so we multiply by 4, which is a total of 34 electrons. When we draw the Lewis structure, we put sulfur in the middle and we bond it to 4 fluorines. Then I fill the octets of each of the 4 fluorines. If I have 4 fluorines, each with an octet, that's 4 8s. 4 times 8 is 32, and 32 electrons have been used. Well, I just found out a second ago that I had 34 electrons, so I have 2 more electrons. Where am I going to put them? Well, I have to put them on sulfur, because sulfur is the only thing that can expand its octet. How do I decide if that was a good idea? Well, I count the formal charge. Sulfur wants to have 6 electrons around it. How many does this sulfur have? 1, 2, 3, 4, 5, 6. Count the dots as 1, count the dashes as 1. This sulfur is neutral. So sulfur has 1 lone pair in the best Lewis structure. 27 says, identify the total number of bonding pairs and lone pairs. And it's important to remember total number in F2. Now, F2 looks like this. It has 14 electrons. It's an F single bonded to an F. There's 1, 2, 3, 4, 5, 6 lone pairs and 1 bonding pair. So the answer is A, 1 bonding pair and 6 lone pairs. So this completes the review for the final exam. Don't forget that the midterm exam is also part of this review. Also, please don't forget that you are allowed a cheat sheet on the final. So please make yourself a cheat sheet and use it. Things like polyatomic ions, maybe charges, solubility rules, and things like this. Rules for Lewis structures, if you want, might be useful on your cheat sheet. Finally, I appreciate that you guys are watching these videos. I hope you find them helpful, and I hope this helps you prepare for the general chemistry lab final.